Alright, this lecture entitled Slow Your Roll will introduce you to the first concepts of kinematic motion. It says the way to catch a knuckleball is to wait until it stops and pick it up, from Bob Euchre. So the learning goal, students will be able to, one, describe the motion of an object based on a position versus time graph. So you're going to have a graph that looks something like this, where you've got position and time, and you want to be able to describe the motion of the object based on what you see on the graph. You need to be able to calculate the average velocity from this graph. So you need to be able to say, okay, I've got this and this, how fast was it going here? And then you need to be able to distinguish between speed and velocity, distance and displacement, and average velocity and instantaneous velocity. A lot of people get these terms mixed up, so it's really important that you be able to distinguish between those two. And then you need to be able to use one of the equations that we will talk about. So, time. Time measures the interval between events. It's usually done with a stopwatch, or in physics class, it's usually more likely done with something called a photogate. And what a photogate is it shoots a laser, an infrared laser, in between these 2 points. And when that laser is broken, it starts the clock. And when that laser is reformed, it stops the clock. Now, time is almost always the independent variable, which means it's going to go on the x-axis. Now, the reason for that is time doesn't really depend on anything at this point. So, you need to be able to say that time is going to be on the x-axis unless there's some sort of strange occurrence. The first thing we want to look at is the difference between distance and displacement. So, distance is the total length traveled. Okay, so like if I start here and I go all the way here and I do these loops and I go and end up in this crazy place over here, the total length, if I were to take that whole thing and stretch it out, the total length traveled would be the distance. It's also what's read by the speedometer, or excuse me, the odometer, which is that thing that tells you how far you've traveled in your car. Displacement, on the other hand, is a vector, okay, where distance was a scalar, displacement's a vector, which measures the change in position between 2 points. So what that means is if you have start and stop, displacement is this straight line distance between the two. So a lot of times people refer to that as the bird flies, because a bird doesn't have to go down streets and around corners and that sort of thing. It just goes from one point to another point. Now, distance says that it's a scalar, which means it's defined by a number only. Where displacement is a vector, which means it needs a number and a direction. So it needs east, left, right, something along those lines in order to make it a true displacement. Now, the reason why distance is not a vector is because you can't say, hey, I'm going up and to the right, and now I'm going down into the right, and now I circled around. It doesn't make any sense. But displacement is a straight line between 2 points, makes a lot of sense. Now, both of these are measurements of length, and they are actually measured in meters. So they do have some similarities. You have a position versus time graph. It says, okay, in the lab, we determined the velocity can be determined by taking the slope of a position versus time graph. That's what you figured out in this investigation. So if you were to take any sort of thing right here, so if we say this point right here and this point right here, you can find the slope between those two things, and that will give you the velocity, or how fast it's actually traveling. Now, velocity is also a vector that we'll talk about in just a second, that it has magnitude and direction as well. The one key thing that you can think about, whenever you have a straight line, the slope is the same everywhere. But that's only whenever you have a straight line. So I can take these 2 points and I can get the slope. I can take these 2 points and I can get the slope. I can take these 2 points and I can get the slope. Any 2 points on that line will give you the same slope value. Example A1 says determine the average velocity between 4 and 5 seconds. So what we're going to do is we're going to mark 4 seconds. I'm going to mark 4 seconds. Oops. So we mark 4 seconds and we mark 5 seconds. So now, in order to find the slope between those 2 points, what we need is we need to know the value of those 2 points. Realize that it's not going to be quite the same as the line, because we draw a straight line in order to get the slope. So if we read this, this looks like it's at 4, 16, and this looks like it's at 5, 25. So whenever we try and find the slope formula is change in y over change in x. Or in our case, 25 minus 16 over 5 minus 4. So you get 9 over 1. So that means the average velocity between 4 and 5 seconds would be 9 meters per second. Example A2 says determine the average velocity of the object based on the graph. So once again, if we're trying to find average velocity on a position versus time graph, we take any 2 points, and it doesn't matter what points you take. A lot of times it's easier to take ones that are actually on lines here. So I'm going to take this one right here, and I'm going to say that that's 1 comma 10. And then I can take another one that's, let's say, right here, and I can say that that is 6 comma 20. Since these are straight lines, it doesn't matter, the slope is going to be the same everywhere. Now, if it were a curve, I would have to look at very specific points. So once again, you do your change in y over change in x, or 20 minus 10 over 6 minus 1, and you should be able to figure out that the velocity in this case is going to be 2.5. 10 divided by 5 is 2 meters per second. Determine the average velocity based on this graph. You should be able to figure out entirely on your own that the velocity is 1 meter per second. And you should be able to do that, and you should be able to prove it for any sort of quiz. Velocity versus speed. Now, velocity versus speed are very similar to distance and displacement. Speed is a scalar, which means it is defined by a number only. Okay, and that's what's represented by your speedometer on your car. Velocity is a vector. It means a number and direction. Okay, and it's not represented by your speedometer. It's actually something you would have to calculate. Sometimes velocity and speed are the same value. As an example, if I go from here to here, straight down the road, I make no turns, no deviations at all, then that would mean that the velocity and the speed would be the same value. Okay, so it says, what do they have in common? They both have the fact that they need magnitude, which is the number. They both can be the same value. But the biggest difference is the fact that this velocity is displacement over time, and speed is distance over time. So most of the times, whenever there's a change in direction, they end up being different numbers. Velocity, if speed and velocity are different, velocity will always be a lower value. Average velocity. So you get to our first formula. This first formula is V average equals displacement over time. It says the relationship between distance, displacement, and time can be seen here, and that velocity represents the average velocity, not the velocity of any one particular point. That's why you see this V average right here. So it says you wake up late for school one morning and walk out of the door at 8:36 a.m. You travel at an average of 45 miles per hour for the 11-kilometer trip. If school starts at 8:45, will you be on time? Realize you have 9 minutes to make this journey. So that's what we want to compare it to. So I have a velocity, that's an average velocity, of 45 miles per hour. The first thing you should realize is that's in miles per hour, and it needs to be converted. Now, the conversion from miles per hour to meters per second means you need to take the number 45 and multiply it by 1609 and divide it by 3600. And when you do that, you get a velocity of about 20.1 meters per second. The displacement is 11 kilometers. You should be able to convert that to 11,000 meters. So now I have a velocity and a displacement, and that allows me to calculate my time. You would say V equals delta D over T. And a lot of people say, but I have the time. Yes, but this is the time that we want to compare to see if we're going to be late. So you have 20.1 equals, change colors just to make it easier to see, 20.1 equals 11,000 over T. Multiply both sides by T, divide both sides by 20.1, and when you do that, the T will cross out here, and then it'll put it up top. The T value, the variable that you're looking for, always has to be in the numerator. You can't ever have the variable in the denominator and solve. But then we divided both sides by 20.1 to cancel that out. And so now what we're left with is T equals 11,000 divided by 20.1. So when you do that in your calculator, you do 11,000 divided by 20.1, and you get 547.3. But realize that's in seconds, and you want to compare it to 9 minutes. So we take 547.3 and we divide it by 60, which is how many seconds there are in a minute, and we get 9.12. So it doesn't look like he'll make it on time. It ends up being very, very, very close. He ends up looking like he's about just about 7 seconds late. So it's possible he could make it, but not likely. Says a runner completes a 10-kilometer race in 22 minutes and 38 seconds. What is the average velocity of the runner throughout the race? Now remember, we always want to answer in meters per second. So the first thing that we're going to have to do is we're going to have to look at what we're given. So we're given 10 kilometers, 22 minutes and 38 seconds represents the time. This is the displacement. So now we can say V average is what we're trying to solve for. We can say that the displacement is 10,000, and you should know that it's 10,000 because we converted kilometers into meters. It's really important that you work in meters and seconds and things like that. So now we go to time, and we see time is a combination of minutes and seconds, and we're going to have to actually get them both in seconds. So what we're going to do is we're going to take 22 and multiply it by 60 and then add 38. And when we do that, we get 1,358 seconds. So now we have a displacement, we have a velocity, we write our equation. V equals delta D over T, or 10,000 divided by 1,358 equals. And when you do that, you end up getting a number like 7.36 meters per second. This last one says a car moves at 20 meters per second for 10 minutes. You should be able to figure out entirely on your own that the value would be 12,000 meters, and you should be able to get that entirely on your own, and you should be able to do a similar problem for any sort of quiz that you may see. Velocity on a ramp. How does the velocity VI compare to the velocity VF on a ramp? So when we did the lab, we were looking at the velocity once it got to the ground. But now we want to know, how does the velocity here compare to the velocity here? And it turns out that the ball is rolling really slow right here and has a much, much higher velocity here. So what we can say is that the velocity here, VF, is greater than the velocity that was at VI. So if we look at our average velocity again, our average velocity can be expanded. Remember, whenever you take an average, what you can do is you can take all the points and add them up and then divide by that number. Well, in our case, we're just interested in 2 points. We're interested in the first point and the last point. If you take those, add them up, and then divide by 2, what you get is you get the average. So we expand this average to say 1/2 VF plus VI equals delta D over delta T. Now, this can be kind of rearranged, and the more common version of this equation is this right here. Delta D equals 1/2 VF plus VI delta T. That right there represents the more common one. This is going to be known as your first kinematics accelerated motion equation. Now, you're going to have 4 of these that you're going to have to be able to use and predict and know which one to use and calculate and all that kind of stuff. What this is saying is that if there is a change in velocity, you can calculate the displacement or the time or whatever using this particular formula. Now, the reason why we say it's an accelerated motion equation is because there is apparently a change in velocity. If there is no change in velocity, say for example it's 10 and 10, well 10 plus 10 is 20 divided by 2 is 10, so you could just use the original equation. This is the only equation you use whenever you have constant velocity. Constant velocity means there's no change in velocity whatsoever. R that's represented by the ball right here that is moving down the ramp, and it's going between two photo gates that are separated by 50 centimeters. And so what we want to know is the car A has the toy car has a velocity of 14 meters per second when it gets here, and has a velocity of 18 meters per second when it gets there. We want to know what the time it's going to take to get between the two photo gates is going to be. So what we're going to do is we're going to start off with our information that's given to us. And our information that gets given to us is we start off with an initial velocity of 14 meters per second. We know that we have a final velocity of 18 meters per second. We also know that the photo gates are separated by 50 centimeters. You should notice that centimeters is right there, so we know delta D equals 50 centimeters, which we're going to convert to meters. There's 100 centimeters in 1 meter, or 0.5 meters. Okay, we want to know what the time is going to be. So now we know our equation that we're going to use in this particular case is going to be delta D equals 1/2 VF plus VI delta T. Now we know we can use this equation here because we know that there's a change in velocity. We know that it's going from 14 to 18. So we're going to go ahead and take our numbers and we're going to plug them into the equation now, and we get delta D, which is in our case is 0.5, equals 1/2 of 18 plus 14 times delta T. Now whenever you attack this problem, remember we want to do parentheses first. So this right here is going to be 1/2 of 32 delta T equals 0.5. Okay, so now what we're going to do is we're going to go ahead and combine these terms, and we're going to get 0.5 equals 16 delta T. We divide both sides by 16, and when you do that, you can simplify it to where it's 1/32, or you can just take 0.5 and divide by 16 in your calculator, and you would get delta T is equal to 0.03125 seconds. Now the next example says you have a car starting from rest. So remember, rest is a key thing right here, and accelerates to 25 meters per second in 60 meters. How long does this take? So once again, what we need to do is we need to go ahead and take a look at what our information tells us. We're given a car starting from rest, so initial velocity is 0. We're given that the final velocity is 25. Now a lot of people get confused here because it says accelerates. Now accelerates in this case just means that it's changing its velocity to 25 meters per second. But since this is measured in meters per second, it is still a velocity, so it must be our final velocity. Final velocity is 25 meters per second. We have in 60 meters, so we have our delta D is 60 meters, and in this case we're trying to solve for time. So when we set this one up, we say 60 meters, or 60, equals, let's go ahead and write our formula first so we know what we're doing. We can say delta D equals 1/2 VF plus VI delta T. So now we plug our numbers in here, and we would say 60 equals 1/2 of 25 plus 0 times delta T. 25 plus 0 is still 25. So then we can multiply it by half, and what we get is we get 12.5 delta T equals 60. Whenever we do this, we can go ahead and solve for delta T by dividing both sides by 12.5. And whenever you do that, you should get a value somewhere around 4.8 seconds. In the third example, you should be able to take this equation right here. You should be able to figure out that it's 60 meters all on your own. So look at the steps we just went through. Go ahead and underline key information, plug the information into the problem, and go ahead and solve for the total displacement.